Okay, so we all love those stories about rockets soaring into space, right? This perfect launches, everything goes right, sticks to the landing, the whole shebang. But, uh, you know what I find even more interesting sometimes?
What's that?
Those times when things don't quite go according to plan. And that's actually what we're diving into today. We're taking a closer look at Isar Aerospace's Spectrum rocket launch.
Ah, yes.
From March 30th, 2025 in Norway. It was a pretty big deal. Europe's very first commercial attempt to reach orbit, launching from continental soil. Unfortunately, though, it didn't make it. But, and this is important, we're not here to dwell on just the fact that it failed.
Right.
Instead, we're going to use this as an opportunity. You and me and all our listeners out there to really get into the nitty-gritty, the complexity of rocket science, and even more interestingly, to see what we can learn from those, albeit brief, moments of flight.
Absolutely. And, when we move past that initial, it didn't work feeling, what we actually uncover is a really valuable case study in the world of rocket development. So what we're going to do today is try to figure out, what probably caused the Spectrum launch to go wrong.
Yeah.
Also, what kind of data, and it's surprising how much valuable information they got, what kind of data they gathered, and then how this whole thing fits into the bigger picture of, everyone else out there who's also pushing the limits of space travel.
Exactly. So we've been poring over all sorts of sources for this, right? You have your news reports, kind of laying out the timeline of events, expert analyses, trying to explain what might have happened. And this is kind of fun. We even peeked into some of the online communities, like on Reddit, where these real rocket enthusiasts are dissecting every little bit of information. And honestly, it's fascinating to see what they come up with.
It is. It's a good reminder that there's a lot of really smart people out there paying attention to this stuff.
Big time. Okay, so before we get too deep, let's set the scene a bit. The Spectrum rocket two-stage vehicle, designed to carry, get this, up to 1,000 kilograms into low Earth orbit. Pretty impressive, right?
That's a lot of payload.
It is. This particular launch was a test, unmanned, of course. And the thing that really jumps out right away is just how short the flight was. We're talking between 18 and 40 seconds, depending on which report you look at. Crazy short.
Yeah, liftoff was at 12:30 p.m. local time from the Andøya Spaceport in Norway. And it's interesting, the initial reports, they all suggest that the very first part of the launch, like right when it lifted off and started going up, that seemed to go perfectly, like as planned.
Textbook, right.
Textbook launch, exactly.
And then, boom, things changed. And all the reports agree on this. The rocket, it started to roll, but not in a controlled way, just uncontrollably.
Yeah, like a spin. And the consensus seems to be that it wasn't an engine problem, but something with the rocket's guidance system.
Okay, so let's break this down a bit. What does it even mean when we say a rocket's rolling uncontrollably? I mean, what's happening there?
So this kind of out-of-control rolling, it often points to problems in the guidance and control system. Think of it like, imagine you're trying to drive a car, but the steering wheel is messed up. You're trying to steer, right? But the wheels aren't doing what they're supposed to. Maybe they're even turning the wrong way.
Oh, I see.
So in the case of the Spectrum rocket, the thinking is that the guidance system either overcorrected, meaning it made these huge unnecessary adjustments, or it was getting bad data from its sensors, making it think it needed to roll when it really didn't.
So it's like the rocket's brain is sending the wrong signals to its body.
Precisely. And, there are a few potential causes. Maybe there are glitches in the software that tells the rocket how to react to the sensor data. Maybe a sensor wasn't calibrated right, or maybe it was malfunctioning. Who knows? Another possibility that people have been talking about is this thing called self-excited roll. It's a mouthful, I know.
Yeah, self-excited roll. What is that exactly?
So basically, it can happen when there are even tiny little differences in what the sensors are saying about the rocket's orientation. So if the algorithms, the ones that are supposed to fix any tiny errors, aren't tuned just right, these small errors can actually make each other worse, leading to bigger and bigger wobbles. And eventually, you guessed it, that uncontrolled spin.
It's like, I don't know, a microphone picking up sound from the speaker and creating that awful feedback loop.
Yeah, exactly like that. A small problem just keeps getting amplified.
And one thing that really struck me when I was reading about this was that the report specifically mentioned that the engines were working. They were actually trying to compensate, right? They were doing this thing called gimbaling, which, if I understand correctly, is how they steer the rocket by pivoting the engines. But it wasn't enough.
It's a really important point because it really highlights that even if the engines are functioning perfectly, if the instructions they're getting are wrong, it's game over. They were essentially trying to fight the faulty guidance system but it was a losing battle.
So it's like, imagine you're trying to row a boat, right? But one oar is pushing forward and the other's pulling back. You're putting in all this effort, but you're just going in circles.
Perfect analogy. And this really highlights something crucial about rocketry. Achieving stable flight during launch. In such a dynamic environment, it requires this incredibly delicate balance, this intricate interplay between the guidance system, the brain, if you will, and the engines, the muscles. And even tiny miscommunications, they can have huge consequences.
That's wild. It makes you realize just how complex this all is. So we've got this guidance system malfunction, but are there any other factors, related to the physics of flight itself that could have played a role in this loss of control?
Oh, absolutely. We need to think about things like the rocket's center of gravity and its center of pressure. These are critical for maintaining stability.
Center of gravity, center of pressure. Okay, explain those to me like I'm 5.
Sure. Imagine balancing a pencil on your fingertip. The point where it balances perfectly, that's its center of gravity. For a rocket, this point is constantly shifting as it burns fuel and gets lighter. And think of a kite flying in the wind. The spot where the wind pushes the hardest, that's its center of pressure. And for a rocket, this point also changes depending on its speed and how it's tilted. If the guidance system's calculations don't perfectly account for these constantly changing points, the rocket becomes much more unstable, like way more prone to tipping over.
So it's a lot more than just pointing the rocket in the right direction and firing the engines, huh?
Not even close. It's this incredibly complex dance between forces, and it requires super precise calculations that all have to work together seamlessly.
Wow. I'm starting to see why rocket science has that reputation.
It's earned, believe me.
So it sounds like a bunch of things might have gone wrong, all stemming from that initial guidance system problem. But here's the thing. Even though the launch was cut short, you mentioned earlier that there was still valuable data collected. So even though it didn't go as planned, what exactly can be learned from a flight that ends so quickly?
That's the key question, isn't it?
Yeah.
What can you salvage from a situation like this? Well, even though the flight was short, Isar Aerospace still managed to gather a ton of useful information. For example, they got real-world data on the rocket's aerodynamics. Like, how did it actually behave in the air during those few seconds?
Real-world data, always valuable.
Absolutely, because it lets them compare their computer simulations and models to what actually happened. They can ask questions like, did the rocket respond to aerodynamic forces the way we predicted? That kind of thing. It's about validating your assumptions.
Okay, that makes sense. I also read that they successfully tested their Flight Termination System. What's that all about?
Ah, yes, the FTS. Think of it as the emergency brake for a rocket. It's a critical safety feature that allows them to safely destroy the rocket if it starts going way off course and poses a danger to people or things on the ground.
So kind of like a last resort safety measure.
Exactly. And the fact that they were able to confirm it worked correctly, even during a failure, is actually a big win. It means that if something similar happens in the future, they have a way to prevent a much bigger disaster.
Oh, that's good to know. That's reassuring. So what other kinds of data were they able to get during those few seconds?
Well, the most important data for understanding why this particular launch failed is going to be all the information related to the guidance and control system. Even though it malfunctioned, they'll have detailed logs of everything, like what were the sensors reading, what commands were being sent to the engines, all of that. And they'll be able to analyze this information second by second, even millisecond by millisecond, to figure out exactly when things started going wrong and why.
It's like having a black box recorder for the rocket's brain.
Exactly. And with that data, they can hopefully trace the problem back to its source, whether it's a software bug, a sensor problem, or something else entirely.
It's amazing how much information they can extract from just a few seconds of flight. I even saw a quote from Isar Aerospace's CEO, Daniel Metzler. He said that every single second was beneficial for data collection, and that even achieving that short flight was a big accomplishment.
It really changes your perspective on what a failure means in this context.
It does. It's like they learned a ton, even if the rocket didn't reach orbit.
It goes to show that rocket development is all about iteration. You test, you learn, you improve. And every flight, even the ones that don't go perfectly, provides valuable lessons.
Okay, so this isn't the first time we've seen a rocket launch go wrong. What happened with Isar Aerospace compared to some of the other high-profile setbacks in the space industry, like SpaceX's Starship and China's iSpace Hyperbola 1?
That's a good point. It's helpful to put this into a broader context. And, the truth is that facing challenges early on in development is pretty common in the space industry.
Yeah, it seems like every company goes through some growing pains.
For sure. Take SpaceX's Starship program, for example. They had multiple failures during their high-altitude test flights in early 2025. Remember those? Two of them involved the upper stage losing control and exploding. Pretty dramatic stuff.
Oh, yeah. I remember watching those videos. It was clear they were pushing the limits, and those explosions were definitely setbacks, even if they were somewhat expected.
Exactly.
Yeah.
And those failures highlighted just how difficult it is to control a large, complex rocket like Starship during those critical phases of flight. And as a result, they faced increased scrutiny from the FAA, the U.S. Aviation Authority, which really emphasizes how important safety is in all of this.
Right, because even if you're pushing boundaries, you have to do it responsibly.
Absolutely. Now, the iSpace Hyperbola 1 failure is another interesting case. The initial stages of the flight actually went perfectly, but then something went wrong in the fourth stage, which led to the mission failing and losing the payloads it was carrying.
So even companies with more experience launching rockets can run into problems, especially when they're trying new things.
Right. It just goes to show that rocket science is incredibly challenging no matter who you are.
So when we look at all these failures, Isar Aerospace, SpaceX, iSpace, what are some of the common themes? What can we learn by comparing them?
Well, one thing that stands out is that early stage development challenges,
Yeah.
especially with guidance systems and controlling the rocket during flight, are really common. It's a recurring theme. And whether you're a new company like Isar Aerospace or a more established player like SpaceX, these failures mean you have to go back, investigate thoroughly, figure out exactly what went wrong, and make improvements before you try again.
It's like a cycle of test, fail, learn, improve, repeat.
Exactly. And it's not just about the technical stuff either. We also see a pattern of increased regulatory scrutiny after these kinds of failures. In Isar Aerospace's case, this was Europe's first commercial orbital launch attempt from within Europe, so you can bet that regulatory bodies will be watching very closely as they investigate and plan for future launches.
Right, because they want to make sure everything is done safely and responsibly, especially as Europe becomes more active in space.
Exactly. And then there's the financial side of things. Repeated failures can get very expensive. Development costs add up, and potential customers might start getting nervous about using your rockets if you don't have a good track record.
It's a high-stakes game, that's for sure. Rocket science is definitely not for the faint of heart. It's complex, it's risky, and it seems like these setbacks are just part of the process of innovating in such a demanding field.
You hit the nail on the head. It's all about pushing the boundaries of what's possible, and that inevitably involves some risk. The key is to learn from those risks and come back stronger.
So what's next for Isar Aerospace after this setback? What are they going to do now?
Their first priority will be to analyze all the data they collected, even from those few seconds of flight. They need to pinpoint exactly what caused the guidance system to fail and figure out how to fix it. It's like detective work, but for rockets.
I bet their engineers are already hard at work.
Oh, absolutely. And they need to figure out if it's a hardware problem, a software problem, or something else entirely.
And how about their morale? Are they letting this failure get them down?
Not at all. From what we've seen publicly, the leadership at Isar Aerospace is still confident. Their CEO has been emphasizing the value of the data they collected and talking about future test flights. They're not giving up.
That's great to hear. They're showing real resilience.
They are. And they're not just talking the talk either. They've already started building their second and third Spectrum rockets. That's a clear sign that they're committed to this program for the long haul.
It's like they're saying, okay, we hit a bump, but we're still going for it.
Exactly. And of course, we can expect them to review all their safety protocols very carefully and make sure they're following all the regulations before they launch again. Maintaining public trust and meeting those regulatory requirements is crucial for them to move forward.
Right, because safety has to be the top priority in all of this. So, despite this setback, what does this all mean for Isar Aerospace in the big picture of the space industry?
Well, even though this launch failed, they still have a big advantage. They can launch rockets from Europe. That's huge because there's a growing demand in Europe for launching satellites, and Isar Aerospace is in a good position to meet that demand.
So they're filling a crucial gap in the European space industry.
Exactly. And this launch, even though it was unsuccessful, shows how determined Europe is to become more independent in space and rely less on other countries. So even though this was a setback, it doesn't change the fact that Isar Aerospace is playing a key role in Europe's space ambitions.
So to sum it all up, we saw Europe's first attempt at a commercial orbital launch from its own soil, and it didn't go as planned, likely due to a problem with the rocket's guidance system. But even in those brief moments of flight, they collected valuable data, highlighting the challenges and learning experiences that are common in rocket development, which we've also seen with companies like SpaceX.
Right. And the key takeaway is that this isn't the end for Isar Aerospace. It's a stepping stone in the long and complex process of space exploration and technological advancement. They learned a lot, and that knowledge will inform their future efforts.
And that brings us to our final thought for our listeners. Imagine this. The data collected from those 18 to 40 seconds of flight could be the key that unlocks Europe's dream of independent access to space. Who knows what other insights Isar Aerospace's engineers might discover as they dig through that data? It really makes you appreciate the long and often unpredictable journey of technological progress, doesn't it?
It does, and it reminds us that sometimes even what looks like a failure can be a crucial step toward success.
And that's what makes it all so fascinating.
Absolutely.
Thanks for joining us on this deep dive. We'll be back soon to explore another intriguing corner of the world of science and technology. Until then, keep looking up.
And keep those questions coming.